for Caitlin, and got it.
Recording for everyone who's not here. There's several people that are interested. So yeah, great.
Okay, so can I share my screen?
You can now.
And now, okay. All right. View presentation. Okay, so you guys can see moving through the slides and everything. Cool.
Yes.
So I wasn't entirely sure sort of how best to structure this, sort of where, different folks were at in terms of like information theory, sort of theory of, structure and complexity and whatnot. So the first like 2 or 3 slides are kind of more philosophical, is not the right term, but more background kind of stuff. And then I'll go in and sort of explain all of the stuff that I did to this data to create what I'm pretty sure are sort of reasonable and usable networks that are, that hopefully will keep us happy for at least a couple of weeks. So starting with the broadest picture, when we talk about complex systems, we're talking about this idea that the whole is greater in some sense than the sum of its parts, right? Interactions between elements constrain their own behavior and the behavior of their neighbors in ways that would not occur if everything was independent of everything else, right? I've heard, some old fogey say, the brain is not an ideal gas as sort of a quip about this, and it's very true, right? That complex systems are interesting because of the presence of structure, and importantly, the hierarchical nature of that structure. And just spoilers, some old fogey was Olaf. He was like one of the first things that he said.
I recognize myself in that very wise statement.
Yeah. And so this hierarchical structure is really interesting because, so say you have some system, which I'll denote with sort of capital boldface X, right? And it's made up of some arbitrary number of individual elements. Okay, these could be cells, these could be neurons, whatever you want. The behavior of the total system is going to be a function of both the individual dynamics of its parts and then the collective dynamics that emerge from the interactions between the parts, okay? And what we generally want to be able to do is decompose those two things into separate sort of categories, right? So just sort of a naive example might be individual neurons have a refractory period, right? Like the dynamics of the brain is in some sense a function of the fact that individual neurons are somewhat autocorrelated. If one fires, it takes time for the individual neuron to recharge, right? But then neurons also are embedded in a network, and one fires, it changes the probability that another one will fire. And so there's a distinction to be made between the individual dynamics and then the sort of dynamics of the structure. And so there's the part-specific sort of information, and then the higher order interactive information. And I like, I'm very interested in how do we tease those apart. And so this brings us to sort of what I call the entropic onion. Suppose that, you pick some random cell, from the xenobot at time t, and you see that it's in some particular state, right? And so variables I'll denote with, or scalar variables I'll denote with a italicized uppercase, and then their local configurations at a given time step will be lowercase italics, okay? And so the amount of information you learn about X at time t by observing it is given by this local entropy measure. And I imagine we're all fairly familiar with this. It's just the negative log of the probability of seeing that configuration, okay? And we call this sort of how surprised are you, okay? If X is autocorrelated, okay, some of that sort of surprise stops being surprising if you know X is past, right? If you think about if it's been raining all week and you wake up and it's raining again, you are less surprised because you know that it's been raining for the last 10 days than you would be if you woke up and, I don't know, meatballs were raining from the sky or whatever, okay? And so we can quantify that intrinsic element level dynamics with the time lagged mutual information. Okay, this is also sometimes called the active information storage. All right. And then similarly, some of that surprise about the state of x at time t could be resolved if we knew the past states of every other element in the system, right? If we know that, some upstream neuron fired or whatever, then knowing that our neuron has fired 1 millisecond later is suddenly not quite as surprising, okay? And so this is often what we're interested in. And you can sort of model this increasingly higher order structure as what Joe Lizier calls sort of an information regression, okay? And so this is sort of the formal way that we can pull apart our entropic onion, and there will be an onion figure here in the next slide or two. So we have the total information disclosed to us by the state of variable x at time t is a function of the information that came from x's own past plus the information that came exclusively from the system around it. So notice that we now have a bold-faced x here, conditioned on our element's own past. So we're not double counting information. And then some intrinsic, entropy term, right? Which could be noise in the measurement. It could be some internal stochasticity if you've got some kind of internal quantum generator or whatever. But these form something like a hierarchy of, or at least these two form sort of a hierarchy of informative dependencies, all right? And so we can just represent this with our little onion figure. You start with some quantity of information that's disclosed by the system at time t, and then you can peel off one of those layers and say, well, I would not be surprised if I knew the past of the system, okay? And this is quantified by this active information storage term, time lag mutual information. And then you can peel away, oops, that's the wrong direction. Then you can peel away a little bit more information by saying, well, if I knew the past of the rest of the system, then some of that surprise would be less surprising as well. And then you're left with this sort of the residual bit of information that is not learnable or shared with either the rest of the system or the element's own past, okay? If you're familiar with Joe Lizier's theory of information dynamics, entropy rate, multivariate transfer entropy, and active information storage are sort of the canonical building blocks of information dynamics. So that's all there is sort of for background and theory, but it provides, I think, a good sort of framework for how I approach these kinds of problems, right? So complex systems show dependencies at all levels, parts, subsets, and wholes. When you're inferring the structure, it's important to make sure that the information is assigned to the correct level, right? Parts level information can be seen from the whole, but should not be ascribed to the whole. So you need to sort of carve out every lower level as you climb up. There's higher order structure that is available when you consider the whole, but not accessible when you consider just the parts. And we typically call this synergy or statistical synergy. And this is all much easier said than done. When you have data, that's finite and noisy, this all gets a lot trickier. Okay, so the rest of the talk, I'm going to talk more specifically about the specific things that I did to extract statistical structure from the Xenobot data. And then at the end, I'll tell you exactly a list of everything I've got produced, and I'm going to upload it all to the Google Drive, so you all can have fun with it. Okay. Any questions so far about all this philosophical jibber jabber?
So far, so good.
Cool. Moving right along then. So the data that I got, these calcium signals, have three aspects that make structure inference sort of difficult out of the box. Okay. The first is that the data are continuous, and information theory is always a little bit more interesting when you have a continuous variable. Their data is clearly non-Gaussian and doesn't follow any other parametric distribution. It's not obviously log normal, it's not obviously exponential. It's just kind of doing its own thing, okay? And the recordings are very short, all right? So I kind of came to the conclusion that I had to pretend at least one of these constraints just simply didn't exist, right? Unfortunately, there's not enough data for a non-parametric inference using k-nearest neighbors. And discretizing the data is, very 20th century, and it throws out most of the interesting information anyway. So I ended up settling on parametric Gaussian information estimators. And so I'm pretending that 0.2 doesn't exist and that we can just model everything as if it was drawn from some high dimensional Gaussian distribution, okay? This actually makes life a lot easier, and why I was biased towards the Gaussian assumptions because almost every information theoretic quantity has some closed form Gaussian analog, right? So given, this should be an exponentiation, not a multiplication. But the entropy is a function of the variance of the distribution, right? The joint entropy is a function of the covariance matrix. The bivariate mutual information is a function of the Pearson correlation. And then transfer entropy works out to just be sort of a fancy form of Granger causality. Okay, so all of these are very simple and usually typically boil down to just calculating covariance matrices or summary statistics like the Pearson correlation, which computers can do very, very quickly. So that's makes a lot of the computational demands of this a lot easier by assuming everything is Gaussian. The other big issue, and I didn't include it in the original set of 3 because it comes back to the entropic onion, is that the data is insanely highly autocorrelated. It's slow and the autocorrelation lasts a very long time. If the each frame is something like what 1 second, that's if I'm remembering correctly, something like that.
Each frame is a 1 second exposure, and between each frame is 5 seconds of time.
Okay, yeah. So if you look at this autocorrelation curve, well, it's still meaningfully non-zero after 5 frames. So that's like 30 seconds of activity. And this presents 2 issues. Okay, so spuriously significant edges, autocorrelation reduces the effective degrees of freedom of the system. And so edges that are not actually significant can look significant. And it can also conflate element level dynamics, that would be the active information storage, with inter-element dynamics, synchrony and information transfer. Okay, and I'll talk a little bit more about that when I talk about effective network inference. But the first thing that I really wanted to figure out when I started playing with this data was, is there some way that I can sort of resolve this issue of autocorrelation? And the conclusion that I came to was to transform the signal into a local entropy rate. Okay, so this comes back to what I was just talking about with the onion. At every time t, our variable x is in some given state, and we can quantify how surprised we are to see x of t with this local entropy term. Okay, if x is highly autocorrelated, we would be less surprised to see particular state at time t if we knew what the state was at time t minus 1. The remaining surprise after sort of accounting for the prior state is the local entropy rate. Okay, so it's the entropy between the state at time t conditioned on the state of time t minus 1. And so for every cell and every data set, I transformed the series from the z-scored global signal regressed calcium signal to this instantaneous local entropy rate. So I'm no longer, so all the time series are now in nats. That's the unit that they're in now. And this new value gives you the novel information generated at time t that is not explained by any of the past behavior. Okay, so this is now activity that could only have come from 2 places. One is intrinsic randomness in the cell itself, or perturbations from some exogenous source. All right, so if we think about the hierarchy, the levels, there's the element level hierarchy, there's the element specific level, and then there's sort of the interactional higher order level. What I've tried to do is basically just carve out everything at the element level and chuck it, so that everything that's left is interactions from sources exogenous to the variable itself. Okay, and you can see this in a scatter plot. On the left-hand side, you have all of the time series for, I think, Xenobot 1, just the immediate past correlated against its immediate future for all k elements. And you can see a very smooth, largely linear autocorrelation function. After whitening with the entropy rate, you can see that it is a completely different shape. And I was a little bit worried that this might be sort of power law-like, that I'd introduced some, negative correlation somehow, but I poked around in these distributions a lot and couldn't really find anything. So I think we can consider the effect of information stored in every variable to be practically sort of evaporated, if not in practice. There's maybe a little bit in here.
Thomas?
Didn't quite survive. Yes.
And there's, I'm guessing there's no way that the exogenous source can be x t minus 2. So even if
So
I'm not
that's
allowed to see my previous step.
That's a good question. I played around with the lag a little bit. It doesn't seem like, lag 1 seems to account for everything. This will come up when I talk about transfer entropy, but the more lags I take into account, the higher the dimensionality of the joint probability space I need to infer. And with very limited data, you very quickly run into undersampling issues.
Okay.
So,
but how do you reconcile this with what you said that the change is so slow? If change is very slow, wouldn't there be a lot of information latent in t minus 2?
not if the information is redundant, because if the information at time t minus 2 is redundant with information at time t minus 1, then if I just condition on t minus 1, I get rid of all of
Get
that.
rid of all of it also. I got it. Thank you.
If there was some kind of synergistic computation through time, then yes, that would be an issue. But for now, it doesn't seem to be the case, and I can't get at it anyway because of the short time series. So this is sort of the best I can do.
Got it.
All right. And so you can actually see what it looks like. I just grabbed 7 time series, and this is the original signal. So it's been global signal has been regressed out. But you can see, the long, there's a spike, and then there's this long tail, right? And it looks kind of like waves or something. After doing the entropy rate whitening, it becomes a much starker time series. If I kind of bounce back and forth, like look at this spike right here, right? You can see that it's associated with a spike in the original data, but all of this heavy tail, is just autocorrelation. There's no, novel information being generated there. So after we whiten, we've almost turned this data into a point process, right? Here, there's a large common spike at the beginning, and there's a bunch of much sharper spikes in the whitened series. And so I'm actually very excited about this because autocorrelation and sort of temporally extended dynamics are a perennial issue when you're doing anything with calcium signaling, which we do a lot of in neuroscience. So being able to get something that looks more like a point process, I think, is actually pretty neat. And I'm wondering what else we can do with this.
There's an application in MRI as well, I think, because there's notorious autocorrelation there too.
Yeah. Same thing, same data set, just visualized a little bit differently. This is now sort of a carpet plot. And so you can see that in the original global signal regressed series, everything is very smeared out. And it's kind of hard to tell, when are things synchronized, when are things, independent. But after whitening, everything becomes a lot more, a lot spikier. And, in the last talk, Olaf showed with the edge time series, how you can get sort of banding behavior. Here we can see banding behavior in the raw data. This is just each row is a cell, no need for the edge time series. And there's clearly, transient moments of very high synchrony. And then maybe longer periods where there isn't as much integration happening.
Can we pause with this point for a moment,
Yeah.
Thomas? I actually want to jump to a question for Doug about this. So Doug, you sent me some raw video of the xenobots forming, and there are periods where it looks like there's calcium flashes like within different xenobots. Like, I don't know if they're communicating, but it seems pretty unlikely. Is there like, speaking of exogenous forces, like if you bump the dish, is there a way that can trigger calcium spikes? Do you like? Is there something else outside the cells that's global that could be causing these global events?
So I'll answer this question 2 ways. The short answer for your immediate question is certainly, I don't think that there's any physical event that could be a confounding factor that is not being generated directly by the bots themselves. I will say that these are developing living systems that are stem cells, and we do see some weird things. I'll try to pull up the video now and post it in chat. But sometimes, because there's cells that are slightly moving and your shape is changing, you can get like aggregation and release of sort of blebs or bubbles where there's some local swelling and then it collapses. And I think when that happens, there is some stuff, right? Some milieu of extracellular stuff that is released into the local environment, which may in fact be capable of signaling locally to both within and between bots. But I would say that, that's sort of an epiphenomenon, but I think even that everything that we see is still generated by the biological system. I don't think we're injecting noise in through any sort of artifacts in the environment or by touching the system or the microscope.
Got it.
And then, also on that point, one of my lab mates in Olaf's lab, Maria Pope, did some really cool work in simulation showing that even, no biology, no, exogenous perturbations, just, metronomes running on a network. If the network has the right general topology, these kinds of, high amplitude co-fluctuation events seem to sort of self-organize for free, essentially, right? We don't have like a formal proof of this or anything, but we're sort of thinking that this may be a general feature of sort of complex systems in action.
And they also have their own signatures that we might want to pull out of these data eventually. So they're not just all on, all off, but they have some topography to them, and they're reproducible, which also suggests they're not exogenously driven, but intrinsically created.
Yeah, one thing I would be very interested in doing is once, with these entropy whitened signals is, so I work a lot with John Beggs, so I'm sure some of you guys know, and we're very interested in sort of cascades of activity, right? And this sort of looks point processy enough that we could start to maybe ask questions of like, can we build a path, from cell A to cell B to cell C, of, I don't know, some kind of some signal propagating into the system. I don't think we have enough data to start asking questions about like criticality or anything like that. But I would not be shocked if there was some cascading behavior in here. But anyway, so there are a few consequences of this whitening that want to be upfront about. So it seems to improve the situation considerably on many axes. So I'll show you some matrices in a moment, but the networks become much sparser, which is good because we talked about how autocorrelation can cause spurious edges. The surviving edges become much stronger, which I didn't really anticipate, but seems like a good thing. And then the edge weights track a log normal distribution much better. If I just do the distribution of Pearson correlation edges from the, or mutual information edges from the raw data and compare that to the whitened data, the whitened data follows a very nice log normal sort of distribution, which at least in neuroscience, we generally think of as a good sign. The big con is that the histogram of the whitened series is even less Gaussian, okay? It's clearly exponential. So I just kept on using Gaussian dependency estimators because, it makes life easy. I could transform the whitened data to be Gaussian, but that feels a bit like cheating. I'm pretty happy continuing to do everything based on Gaussian information estimators, but I figured I should at least make this, cards on the table that we're now really stretching that assumption.
Does it just feel like cheating, or is it cheating?
That really depends. If you're an artificial intelligence person or a data scientist, and all you care about is, making something that, that will work in a regression. Yes, people do this all the time. There are well-established transforms to go from basically any distribution to any other distribution. In terms of like making a biologically plausible model of, a system from the data that we have, it becomes a question, which is introducing less weirdness, right? Gaussian estimators of an exponential process, or taking a process and like torturing the data even more to bring it in line with, what estimators we're using. I don't have a good answer for that, but, it's just something that kind of sits in the back of my mind because I feel like we often play fast and loose with statistical assumptions in life sciences. But anyway, we can talk about that at the end. So here you can just see two FC matrices. These are from the same data we saw before. This is bot 1 phase 1. In the GSR only functional connectivity matrix, it's very dense. And, the highest value edge is about, 1.3 maybe. After whitening and, doing the same, mutual information in NATs, the highest edge is like four NATs, and the system becomes a lot sparser. So I think what's happening here is, there are a lot of things that look connected because of the autocorrelation, but what's really happening is just that, the reduced degrees of freedom are sort of laundering an apparent statistical relationship through significance testing. And I should say that every edge passed Bonferroni corrected significance tests. So I set my initial alpha to be 1 in 1,000, and then I Bonferroni corrected on that, which works out to be about 10 to the minus 8. So these are highly significant edges. And so Olaf talked a little bit about this at the last talk, but what could we do if we just stopped here, right, and looked just at functional connectivity, right? There's a lot we could do. Community detection, rich clubs, assortativity, nothing path-based. I think there's some people have an instinct to reach for like a small worldness index, and that's something that I at least, and I think Olaf is with me on this, I'm very opposed to. You shouldn't run paths on statistical networks because it doesn't mean anything. There's also all of this higher order integration, segregation, redundancy, synergy work that we've been doing. I think, Michael, you saw on Twitter, we just had a preprint like the day before yesterday, looking at these things like TSE complexity, O information, total correlation. So this is at the top of our brains right now, and be pretty easy to look into.
I feel 30 years younger doing this work again.
Oh, that's good. Remember that when you're writing my letters of rec, we'll bring youth, we'll de-age you, if you hire this person. And then so, in the same way that we could do edge time series, Olaf talked about that last week, we can also do local mutual information for every edge. It's functionally the same thing, just the statistics are a little bit different. And then we can also do things like local total correlation, local O information, and there's quite a bit we could dig into there.
So, sorry, can we actually do all this without going to Gaussian assumptions? I mean, I thought just a moment.
No. This is all Gaussian assumptions. I just
so yeah. but you said earlier you weren't going to do that, or you thought there was cheating involved or something. Oh, or you?
Oh no, sorry.
I missed the transition there.
Yeah, transforming the whitened, so the whitened data is clearly exponential. Okay. Forcing it to be Gaussian just to satisfy this correlation, that would be cheating.
Okay.
Okay. I think sticking with the Gaussian assumptions, even though the data is not Gaussian, is not optimal, but certainly fine.
Okay. Well, I mean, it's still a bit of a stretch, but okay.
Yeah. Unfortunately, there's no well-developed like parametric, like a joint exponential distribution. What does that mean? There's no parametric mutual information for that. So unless we wanted to go and do things like really discretize, go discrete, this is kind of where we're at, because we still don't have enough data for a Kozachenko-Leonenko or a Kraskov estimator. But anyway, I think there's plenty here with the functional connectivity that could keep us happy for a long time, but it ignores the system dynamics, right? If you were to shuffle all of the frames, the statistics, mutual information, the resulting network would all be the same. So how could we take dynamics into account if we wanted to, all right? And so now we're moving from functional network inference to effective network inference. And for people who don't know, functional connectivity is just looking at instantaneous co-fluctuations, whereas effective network inference is looking at how knowing the past of one variable reduces your uncertainty about the future of another variable, okay? And the usual approach to doing this is the transfer entropy. There were transfer entropy networks made with these, so I don't think I have to go through in detail what it is. You can kind of think of it as the information that knowing the past of x1 discloses about the future of x2 that is not disclosed by x2's own past. Although that actually turns out to be not entirely true for reasons that I'll get to in a little bit. I tried doing transfer entropy and it was an abysmal failure. Okay, so I was using Gaussian assumptions. I only did a single lag. And almost no edges survived FDR corrected significance testing. Again, I set my thresholds to 1 in 1,000, and then Bonferroni corrected on top of that, which brought me down to like 10 to the -9 or something. And something like over all of the data sets, I think maybe 4 edges survived statistical significance testing. And I think this happened because the lag1 transfer entropy requires inferring a 3-dimensional probability distribution, right? You need the past of x1, you need the past of x2, and you need the future of x2, okay? And I think there's simply not enough data to infer a 3-dimensional Gaussian reliably, okay? There's also the problem that having all of these terms in one probability distribution means that transfer entropy conflates synergy between computation and the true information transfer, okay? And this is because conditioning is not necessarily a subtractive operation, right? People think conditioning is the same thing as sort of controlling, but it's a little bit different from that. And if you're conditioning on a collider, there's all kinds of weird synergistic effects that can emerge. However, all hope is not lost, okay? I think the local entropy rate whitening helps us get to function in the same place without having to worry about some of these issues, all right? So I apologize for the wall of text, but this is less painful than trying to write it all out in mathematical notation. So normally, we don't use time-lagged mutual information because it conflates synchrony with information transfer, okay? If x1 and x2 are synchronized, knowing the past of x will reduce our uncertainty about the future of x2, but x2's own past will also do that, right? So you can see how if the system is synchronized, there can appear to be information flow, but it's not, you're ascribing a local dependency to the higher level interactive layer, right? Coming back to our entropic onion, all right? So that's what the transfer entropy is supposed to do. You're supposed to condition on the past of the target to ensure that you're only ever getting the information that must have come from the source, okay? But because we've scrubbed all of the autocorrelation out of our time series, the past of the target discloses no information about its own future, right? I could go back to that scatter plot I showed before. There's no information storage in here, okay? And so that puts temporal mutual information back on the table because there's no risk of conflating information storage and information transfer in this way, because we've just erased any possibility of information storage occurring at all. This also means that we never have to deal with a probability distribution with more than 2 dimensions. We need a 2-dimensional probability distribution to do the edge whitening, and we need a 2-dimensional probability distribution to do the mutual information between the source and the target, okay? But we never have to we never need a 3rd variable at any point. We're doing 2 and 2 instead of 3, okay? And since there's no direct interaction between the past of x1 and the past of x2, they never appear in a probability distribution together, I'm like 85% sure that the possibility of a synergistic confound with respect to the target's future is reduced. All right, so if I'm being perfectly honest, I'm rather pleased with myself that this all worked out, if it has worked out as well as I think it did. I think we've killed like 3 birds with 1 stone here. And so this all works on very sparse, very autocorrelated data.
So Thomas, I was going to ask something along those lines. So this itself is algorithmic innovation, right? Aside from the Xenobot data itself.
I mean, I won't claim like all of it. People have used local entropy rate to whiten time series in the past. Robin Ince did something like that. And there was just recently a really cool paper I saw on Twitter looking at video compression. You can use this when you're compressing video, but the insights about what this might mean for network inference and controlling for synergistic confounds. Yes, this is all I think. This is all novel as far as I can tell.
Great.
Robin Ince may disagree a little bit with that, but he's nice. I like him. And then so for the effective network inference, what I did was for every pair of cells, for every lag from 1 to 9, I compute the time-lagged mutual information. I find the lag that produced the largest value, And then if that value is significant after FDR correction, that should be a -9, not a -8, then I add it to the network, okay? And so here you've got an effective connectivity matrix. The range of values is about the same as we were seeing in the functional connectivity, which is nice. It's a little denser than I thought it would be, but that's fine. And then I also have for each matrix, I also have the lag that gave you the associated edge.
It is not as dominated by the degree, I think, as the previous TE networks were. So it's got more of some sort of a balanced upper lower diagonal. I mean, to my eye, it looks a little nicer, to be honest, than what I had seen with the previous transfer entropy.
Yeah, there are. I mean, so I don't want to throw shade at whoever did the previous transfer entropy network inference, but I think for the sort of the statistical problems that I've detailed before, I think this is a more principled way of building an effective connectivity network. There are a couple of sort of I don't know, sanity checks that somebody, probably me, should do with these. So for instance, it would be really nice if the maximum lag fell off with distance. You'd think that two cells that were right next to each other, it would take less time for the highest interaction to occur, and then far away cells would have larger lags. I haven't done that yet, so we just need to unpack the XY coordinates and whatnot, but that would be easily doable. Also, each lag appears about the same number of times. There are as many edges that are significant at lag 1 as there are at lag 8, which I found a little bit odd, since lag 8 is like well over a minute in terms of like the actual time spent, from frame to frame, like in terms of seconds. So there may be some question about what our maximum allowable lag is. I just picked 1 to 9 because it was a nice interval, but I would personally have more faith in some of these low lag terms than maybe something that took 9 frames to propagate across the system. But again, I have is sort of bring in questions of biological plausibility and things that I have no context for. So
did you ever compare these previous, pre-injury versus post-injury, phase 1, phase 2?
I've computed all of that, but I haven't. My focus has been totally on the network inference sort of pipeline, analyzing any of the things that come out. Haven't done any of that at all.
Thomas, can I ask about your mentioning sanity check? So if you're kind of trying to road test some of these methods so that we can claim what we're seeing here is real. I mean, and also this is on one xenobot, can we do this again on the other 8 xenobots? But I don't know how much is known, Mike and Doug, about like, do you expect all the xenobots to react similarly to injury, or is that just not known? Like, what would be the default assumption here, that they should all behave calcium-wise more or less the same after injury, or not?
I would guess that this is speculation, but based on sort of some preliminary knowledge of the wound healing literature, is my guess they will be similar-ish. There will be a standard deviation bar that's due from interbot variation, as well as my injuries are manually done. So no 2 injuries are going to be the same. I may poke deeper, or maybe a slower injury. So I think that will be a second source of variation, but my guess is you could bracket these with some sort of error bars, and we would be able to estimate a plausible range of what it looks like.
Got it.
So this actually, I'm basically at the end of the talk. What could we do with effective connectivity, network analysis, mostly community detection, bridge club, all the good stuff. In the same way that we can do edge time series and local mutual information time series, I can do local time delayed mutual information time series. And so we could look at positive and negative, informative and misinformative moments. We could look at the triadic synergy, which is something that we have spent a ton of time at IU sort of refining, although it's hard for continuous data. Here you find in the network triads with 2 sources synapsing onto 1 target. And then you can do the partial information decomposition of the joint mutual information between the paths of both sources onto the future of the target. And you can break that down into redundant, unique, and synergistic components. This would require another three-dimensional probability distribution, which I'm not entirely comfortable with, but I figured I'd throw it out there since it's something that we've done a lot of. And then maybe something to do with propagating signals. Can we, if the spike occurs, in one, can we follow it through, the rest of the system? I have no idea if that's plausible or not, but worth looking into. And then, so the data that's being shared, all right, I've generated about 200 files that at some point, I'm going to upload onto that Google Drive that Caitlin gave me access to. So I've got the raw time series as a multi-dimensional array in CSV format. So this is the same as the data that Caitlin sent me. It's just it's in a time series form as opposed to the columnar form it was before. The same time series after doing global signal regression, the same time series after entropy rate whitening and global signal regression. The Pearson correlation functional connectivity matrices, which are signed, plus the associated p-value for every edge. If you wanted to play with the thresholds, you could do that because all that information is stored. The Gaussian mutual information functional connectivity matrices, which are unsigned, plus the associated p-values. I did a pre-thresholded mutual information and Pearson functional connectivity matrices, just, we want to just hit the ground running and wanted everything significance tested outside the box. And then the effective connectivity matrices, their lag matrices, and the associated p-value matrices. And those are both, I have p-value matrices, dense matrices, and then pre-thresholded effective connectivity matrices as well. So this works out to be about 200 CSV files. If anybody wants to know, I can talk about the naming schema, but it's pretty obvious if you look at what the files are. And so the idea is that at any point in the pipeline, from raw time series all the way down to effective connectivity lag matrices, you can jump in at any point and say, well, this is where I'm interested in, or maybe I want to try a different path in the branching tree of network inference pipelines. And so you just find a place to jump in and go off in your own direction. So yeah, that's what I've got. There's that's what I got.
Fascinating, Thomas. This is amazing. I learned a lot. Thank you.
And so the other hope is that anybody, I'm putting my neck out, I'm putting my neck on the line for the correctness of the matrices, right? Anybody else should feel comfortable taking these matrices and doing what they want. And if some reviewer says, well, your network inference is dumb, well, that's on me now. You guys should feel free to go nuts without having to worry about where any of this came from. I worry about it for you.
Great. I mean, I will definitely take a look at those CSVs at some, very soon to do some of the network analyses that I was showing last week, but do them again, basically. Because this whitening step really helps. We talked about this last week also in the lab, and Thomas kind of gave the entropic onion made an appearance on the whiteboard, and we all had a lot of good laughs about that. So I think it really helps to remove those sources of autocorrelation, which in this particular data set are very, very much up in your face, and you really want to get rid of that. So, so some of the things that I showed last time, community detection, core periphery structure, I think I want to revisit that now with those newly configured effective connectivity matrices, and maybe also the functional connectivity.
Is there a way to compare these results with a sort of null model where the assumption is the cells do not communicate and they act independently? Do we need more experiments to do that, or is there a way to just scramble the data or do some stats or just data science to create that null model at all? Just a general question.
So yes, and that's probably something that we should do at some point, although you took Olaf's class, right? You know that the null model is often the harder thing to game out. I think the default, the easiest thing to do would just be some kind of circular shift null model where we take the whitened time series and just sort of rotate them around independently and then re-infer the networks and see what they look like.
this will preserve the autocorrelation to the extent there is still any left, but it will destroy the covariance. It will destroy the interactions, and you would do that 1,000 times or 10,000 times, and then compute a network from that. It's a fairly liberal null model in the sense that you really do away with temporal precedence queues entirely, but it preserves sort of the rate process on each node. It sort of preserves what each node does. You just rotate it.
So if you were to do an actual experiment where we say, I don't know, inhibit the gap junctions or the microtubules or something and generate the data, would we expect to see something similar to what we would get from all this scrambling? I don't know.
To my mind, that's an experiment. That's not a null model anymore. A null model is some statistical thing, right? Where you shuffle bits and bytes and you look whether your hypothesis holds up. It's a good idea to maybe do an experiment where you shut off intercellular communication, gap junctions, or something like that. But that's something that would require new experiments. That's not really. I mean, that would be itself require a null model down the road, to whatever residual thing you're getting is that above chance. So.
Yeah, and I'm just trying to imagine if there is a situation where such an experiment would generate a data set that cannot be captured by all this scrambling or
exactly
null model. But I don't know. Yeah.
So at some point, I mean, Thomas and I are kind of trying to help with some of sort of our expertise here, but you guys, especially Josh and Mike and Nick also and others, I mean, you have been thinking about this paradigm and this construct for a very long time now, and you probably have in mind some sort of big picture idea that you want to get across with this. And so that to me is important to consider. What is it that you would need to demonstrate a capacity or a response or something like that, something that you're looking for in these xenobots, right? That's sort of where I think neither Thomas nor I really can speak much to that because we're fresh to the game here.
Yeah, just echoing that, I have everything that I've presented, is completely domain agnostic, right? Entropies, it's all probability distributions at the end of the day, which is nice because you can plug it into almost any system, but it also means that you have no domain expertise to speak of. I have very little domain expertise in anything anymore beyond multivariate information theory, which is a big enough field to keep me happy for a whole lifetime.
We should probably dedicate a whole, other meeting to exactly this. Like, what I know Doug and Mike have a gazillion questions. I will just shove one in from the robotics point of view. If you view the xenobots as robots, these are the first robots in history that you get stuff for free, right? So, Doug cut this robot almost in half and it spontaneously healed itself up. We didn't design the robot to do that. I didn't know it was going to do that. I don't know if it does it every time, but if we could extract what's going on, in terms of structure and dynamics, and build that back into the AI design system, so it knows that if you want a xenobot to do X, Y, and Z, and you want it to inherit this ability from Frog, make sure that you have blah 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 blah. Like, why is it that the xenobots, inherit this from the donor Frog? If there's any way that the network analysis can make predictions as a roboticist, that would be huge.
You're almost like a neurologist or a psychiatrist who has a patient come in the door, and you want to know what is it that happened, a month or a year or 10 years ago that took that person on that path. What makes some people be more resilient to a challenge than others? And in this case, of course, you have the before state. You can actually observe these, and you can even design them down the road, right? I mean, that's a really good question. I like that.
I would also just add real quick, 2 quick notes. From even a system of, does evidence exist that this is a real thing, that this is real information? I think there's a strong literature both within and between. So within, if you're talking about an embryo or a frog where these are derived, repair is an expensive process, and there's this idea that when you're injured, you turn on a bunch of signals to help repair, and you keep it for a certain amount of time, and then you shut it back off. So it would be interesting to look at in a system like this with repeated injuries. Are you sort of prepping the system? Could we even look at a network and make a prediction? How recently was this injured? How many times was it injured? I would say even more wild, I know this literature much better, is there some really cool injury information in all vertebrates I've looked at. So salamander, fish, and frog, where if you have a bunch of eggs and they are injured, so if a predator comes and eats some of them, or if there's an infection, the other embryos can actually speed up their development twice as fast to try to hatch out so they get away before they're eaten. So they are actively getting information from their neighbors on injury states and making developmental changes to speed so they can speed or up or slow down, which is super crazy. But selection has produced the fact that these signals can be interpreted over fairly sophisticated distances. So just to ground this in, like, there is already existing literature that shows that this type of information can be used in the system over the types of scales and timeframes we're looking at.
And so two quick things to add. One is following up on what Doug said. We have this, I don't know if you guys remember, but I could show this video next time. Patrick, I think Patrick was the first to see this, that when you have three bots sitting in a row, not touching each other, you stab one, there's a calcium flash. The other two, in some small number of seconds, the other two will light up progressively. So you can actually see this wave, like this injury wave, cross. And we have a paper. Megan is working this up to some level of detail. So there's that. There's the interpretation of the damage information by a conspecific that might be sitting nearby, right? So can we watch embryo A to learn what happened to embryo B? That's kind of one thing. And another thing is that kind of back to what Josh said. We have some data that Pi is analyzing now, which is all the genes that are turned on in xenobots that are not on in frog embryos. So the other way around is not informative because, of course, they're missing all kinds of cell types. That makes sense. But what new genes do they turn on that normal embryos do not have? So I think, within a couple of weeks we'll have that information. So that may help address. I mean, it's not calcium signaling, but it may be relevant to address the issue that Josh was talking about, which is what do they inherit from the frog, and what is novel? What's novel? What are the genes that are coming on that normal frogs don't do?
I think mapping all these networks on the physical space of the embryo and locate the point of injury and visualize the calcium across the embryo could generate some hints as to what's exactly the kind of information being processed and what sort of cognition is happening. I think when we have that map, that would be really cool. Yeah.
So I would say we need to wrap up now. I would say, why don't we start next Friday, assuming Olaf and Thomas and Doug and Mike can make it, that now that we have this fresh in our minds, we actually try and sit down and say, what do we need for a first publication on this? Doug, do you need to actually go back and do any more experiments, or do we have enough on hand to say something intelligible for biologists and computational math folks, or not? It sounds like I feel like we're close, so we should maybe see what we can do.
My note was the only thing I could think of. Maybe we'll just save it for next week. Let's not even dig into that.
Okay.
I'll put it in the Slack.
Okay. I recorded this so we can watch and be ready. Well, we'll just take a little bit at the beginning of next week's meeting, because
just a real quick question. Do you have a lot more recordings, or you shared, say, 6 data sets, 3 of which were rather small. In terms of the coverage, do you have a lot more sitting on file somewhere, or was this just a sample, a teaser, a trailer, or sort of an appetizer, or do you have a lot more?
I have a link. I pulled all of the ones that I have and sent them the links to Caitlin, but I will share them with you as well. I was going to say the one thing that might be useful for me is just to run one experiment where I capture calcium data at the fastest rate possible over like 24 hours. And that way, if you have sort of the maximal data set, we can always subsample different amounts of frames, different time periods, to see if we're missing something or not.
Right. Yeah. But the short answer is you have a lot more.
Yes, I will put those in the Slack right now.
That was what I was angling for. That means there's a lot more to work with, which is great.
So Thomas, you can use Caitlin as the go-between for that. Okay.
Cool.
Fascinating. Great stuff, everyone. Thank you, Thomas.
Super.
Yeah.
Thanks
Nice
so much.
talking to you guys.
Have a good weekend, everyone.
Bye-bye.